Start recording. Okay, so I've started recording. Welcome everybody to the afternoon, day 7. Force and power and energy calculations. Just everything about basics of force, power, energy, the relevant quantities that we need to know in the physical world around us. So I kind of connect this to numeracy, the idea that we can count things, so counting things like atoms or velocities and forces. It's important so that we're actually getting into the realm of engineering and understanding what's happening, as opposed to hand waving. When you can measure something, you can understand it more deeply, so it gives you additional information about phenomena. Force and power are important with many of the machines we study. If you want to do a certain task, you need to provide a certain amount of force or power to that task in order for it to be done efficiently. You can calculate how much force or power something has. You can calculate things like efficiency and have a deeper insight to whether something that you're designing can work. So it's part of making calculations happen. If you do calculations, you can predict some of the phenomena that are going to happen in a thing that you're building, as opposed to you get into something and it may or may not work. You'll kind of have an idea of how well something will work. So having numeracy, or the ability to count things in a physical world, is very important, and this kind of numeracy is the basis of engineering and physics. Let's start with F equals ma. So force equals mass times acceleration. So that's a basic equation of physics. What does that mean? That a force, if something has a mass, that mass divided by how fast it accelerates is a force. That's in the mechanical systems. There are forces that are electromechanical, there are thermal forces, there's pressure, there's many different kinds of forces. And you can talk about forces of bulk ensembles, like a human body. You're running 20 miles per hour or something. Or the velocity of individual particles. With individual particles, that is called temperature. How fast individual particles in a gas are moving, you would call that not the velocity of individual particles, because you don't really care about the individual particles as much as how fast they are moving on average as an ensemble. So you have the idea of quantifying things as individual bulk objects like people and cars, or individual things like atoms of water or gas for its temperature. Basics. What are the kind of forces that are out there? I mean, besides just mechanical force, there's other types of forces that come from gravity, from acceleration, which are mechanical forces. Forces that come from electricity, from magnetism, from light, sound. There's pressure, radiation. There's chemical forces, like how individual molecules can react with one another. There are nuclear forces, thermal, and they can be, when you get down to a super micro scale, you get into quantized forces, where you're starting to talk about individual particles as opposed to ensembles of particles. Like a human body is a large ensemble of particles, and it works like a bulk object. Whereas when you go down to the very detail, down to the individual atoms, you get into quantum effects, which means forces that are on the particle level. So in general, when you talk about human visible things, you're talking about like Newtonian motion, as opposed to quantum physics, where quantum things are for very, very tiny things. And so, for example, in a real world, you cannot walk through a wall because your body will be blocked by it. But in a quantum world, actually,
you're guaranteed to walk through a wall.
You can walk through a wall. There's effects like quantum tunneling, which say that there's a finite possibility that you can actually go through an energy barrier such as a wall. But now when you take a look at bulk objects such as humans, the likelihood of you going through a wall, it's actually not zero, but it's very, very low.
And if you ever do,
And if you do, you will find out that it is very low. So forces can add. There's basics of forces that you can add forces, one on top of another. If you add forces in parallel, they will simply be additive. If one force pushes against another, then that can balance it out and provide no net force, even though there's, say you're pushing an object from two sides equally strong. I mean, a lot of energy may be expended on that, but you don't have any actual motion. So additivity and subtractivity of force exists. We also conserve matter and energy. Like, for example, you cannot plug a power cord into itself and create infinite energy. There has to be a source and sink. Continuity of fluids is a big concept with forces, where today, for example, we ran the tractor to run the ironworker machine, and we had it connected with one hose. Well, that is not going to work. You need continuity of fluids. Motion has to go in a circle if you have a closed loop circle. So let's talk about basic things like velocity. So what is velocity? Velocity is a change of position in time, like dv dt. In calculus, change in velocity over time. So you have position, then you have velocity, and then if you change velocity in time, you get acceleration. Acceleration is what, by force equals mass times acceleration. Acceleration is what gets you force. If you're moving at a constant speed, there's really no force, unless, like, for example, friction is slowing you down. That's a force that's slowing you down, so you would have to exert some force to keep moving at the same speed. But ideally, in vacuum, if you're moving, you have no force. Like in space, you go launch a rocket, it'll in principle go forever if there's no resistance. So there is no force. But if that rocket decides to accelerate, there will be a force at that point that you can feel. When we talk about velocities are very important for our understanding, because in the kind of work we do, you want to know things like what's the velocity of a tractor, like when you use a certain hydraulic motor on wheels, how fast will it go? You can calculate those kinds of things. You like to know things like acceleration, like, for example, if you're designing a CNC torch table and you have certain stepper motors and you have a certain tool head, you want to know, okay, given that the force that the stepper motors can exert to move an object, how fast will a mass accelerate? Well, it doesn't go from 0 to 1 immediately, 0 to full speed. A force will be enacted over time, and that's acceleration. In 3D printing, we also care about jerk, which is the change of acceleration in time. You can actually, in 3D printing, have that as one of the settings. So say you're accelerating, but you might be accelerating faster at one point than another. So I haven't really run into that until 3D jerk until 3D printing. I've never actually heard of it in school, but in 3D printing, it is actually quite relevant.
You mean impact, right?
I'm not sure.
Jerk and impact.
I'm not sure if that's what it is.
Jerk is a particular word. I don't know whether or not it's the same, whether impact has the same meaning.
No, I don't.
It goes position, velocity, acceleration, jerk, super jerk, and I'm not sure what comes after that, if anything.
Okay. Yeah, and we can, like after like accelerations of acceleration of something, like how far do we go? Where does it make sense? Well, we do have to consider some acceleration of acceleration, change of acceleration over time. Yeah. Now pressure is a very important quantity that we need to know about. Like in hydraulics, we deal a lot. That's basically about creating high pressure on the order of thousands of pounds per square inch. I'm kind of more familiar with pounds, so sorry for the MKS guys. Pressure is relevant to things like a rubber tire. For example, if you want to know how far a tire will deflate under a tractor, you can measure, you can say, okay, I've got certain pressure, which is pounds per square inch. Well, if it's, say, 50 psi, how many square inches do you need to sustain that? So basically your tire will flatten out
To that 50 square inches.
to that the number of square inches that corresponds to the force of your entire tractor. So you can actually calculate, like typically say we inflate tires to say 50 psi or whatever, well, you can actually get a feeling for what that quantity will be based on the weight of an object. We also have concepts, so like for example gravity. You can store energy with gravity. So now we're getting into how do you so after force is energy, you can talk about energy. So energy equals force over a distance. So for example in gravity, which is relevant to things like gravity storage, this is actually a little map of our facility here, where we're saying, okay, we're going to put a lake, a little pond. Oh yeah, share my screen here. A lot of this is very conceptual, so you kind of get the 101 on forces and energies. Let me share my screen. Okay, so take a look at this. Storage of, so energy is force over a distance. So what is for gravity storage? This is an example. So force over distance, meaning you're lifting water, so you're exerting a force to lift water up a certain distance, and you have energy, so mass times gravity times height, mgh. So force, which is mg, mass times gravity, times height. So mgh is the energy stored in a pond. So here we have the water runoff of our facility, and here I selected, you can see some numbers here, but you can actually calculate things like, okay, if I put a 1/4 acre pond uphill and then make it go downhill, well, you can calculate the mass of a lake by taking its volume and multiplying by the density of water, which is 1 kilogram per liter. I don't know how much it is in pounds, because something I know in MKS. But you can calculate the weight of the water, and then you can estimate from a land map here the contours are height contours, so you can see the height that you raise the water. So say you pump water for energy storage, nighttime energy storage, from 2 to 1. So say in the daytime with PV or whatever, say you're in a photovoltaic kind of a system setup, you can pump water, store it, and then release it at night using mgh, the amount of energy. And you can see that I kind of did some basic calculations there, and under certain assumptions there, that what do I have there? It's a quarter, let's see, did I do a 1/4 acre, or was it, yeah, 1/4 acre pond, 6 feet deep. If you go through that's about 2,000 cubic meters of water, but that will get you 24 hours of 1 kilowatt of power. So that's kind of like another way to use water for energy storage. We talked a little bit about energy storage in saturated water yesterday, but you know, if you have this kind of numerous, you can start calculating, okay, can I put a pond on my property and actually use that for water storage and energy at the same time, and irrigation? So talking about integrated system design to make this into a paradise where you've got perennial polyculture, you got energy storage, you're using water, you're using soil, plants, rocks, the basics of civilization to make a modern day civilization that's ecologically centered. There's also chemical energy. Chemicals store energy. Reactions of, like for example, coal or carbon or wood has actually an intense amount of energy stored in it. So in that case, you're going from solar energy getting converted into chemical energy that can be then released as heat by burning it to do things like running engines, running gasifiers, or burning it in external combustion engines like steam engines or Stirling engines. So chemical energy is a very popular way to store energy. In fact, currently all our civilization is based on the chemical energy of carbonaceous fuels like oil and coal. Energy density, that's a good thing. So to understand how much energy density you have is important, because you can then compare one fuel against another. So Einstein also came up with the idea that E equals mc squared, and that corresponds to the nuclear energy of atoms. So if you got a mass of something and you nuke it, you make it undergo a nuclear reaction such as fusion, you can smash atoms together and they will release energy on the order of E equals mc squared. So you can convert a certain mass. So in energy density, nuclear stuff like fusion, now they actually have antimatter is the most dense. I've never talked to antimatter, so I don't know what it is, but I know a little bit about deuterium, like plutonium. It's what?
I saw antimatter in the Pizza Hut.
Yeah.
Oh.
You know, I'm sorry.
Manny saw some antimatter at Pizza Hut the other day, but I haven't seen it.
Anyway, I just read about jerk. It's the first time I hear it.
Yeah, yeah.
The only time I use jerk is for a person.
Right.
No, I
Yes.
said, what the hell
That's-
is jerk? Is
Very
it
quick
second
acceleration.
derivative of speed?
Changing
Yeah.
I never
acceleration.
knew that.
Yeah.
You
Well, that's
sure?
what I was going to say. So, moving on, energy density is important to understand because then you can consider things like, oh, is there enough energy in compressed air? Is there enough energy in charcoal or wood or gravity storage? So you can start getting an understanding of that. Here the energy density on Wikipedia talks a lot about just chemicals. So here it's all chemical, including antimatter, just so particles. Deuterium refers to its nuclear energy, like in a fusion reactor. So you're going to have nukes first as the highest energy density. So that's why people like nuclear power, because it's super energy dense. Out of small amounts of matter, you get intense amounts of energy. However, we haven't figured out what to do with the waste, including fusion. Like people say that fusion is clean, but it's not, because in fusion you always generate neutrons, and neutrons, when they come in contact with matter, they make things radioactive. So like deuterium, that's great, but humanity doesn't know yet how to not create radioactivity in nuclear fusion reactions. So let's move on to further options here. Let's get beyond the nukes like plutonium. Let's get to hydrogen. So right after all the nukes like plutonium, uranium, thorium, deuterium, you have hydrogen. So hydrogen is extremely energy dense if it's stored in a liquid form. Now, liquid form hydrogen is, you have to use a lot of energy to liquefy it, but you can also compress it. So you can see how the energy content of hydrogen decreases. At high pressure, yeah, it's got a lot of energy.
How can we make it safe?
It's already safe. People have figured out how to store hydrogen safely since about 20 years. So
You mean it's not liquid completely? If it's a spark, it's not going to affect it. So it produces slowly as you use your car. Like in a form that you can produce it slowly as you use it. Not stored in a tank. This is what I mean.
yes, but then you're using...
It's always dangerous, you know?
It's not always dangerous. It's comparable safety to gasoline tanks. Read Soft Energy Paths by Amory Lovins. That's a seminal book in the field of renewable energy. Hydrogen happens to be renewable energy. You can burn water. You can split water. And then what you get out of that is water back after you burn it. You do store it. You can store it as a gas, but you have to be very careful. Compressed gas, but you cannot have any mixture of hydrogen with oxygen. But that technology does exist. I haven't done any hydrogen outside of just little experiments, but I do believe that hydrogen, if you look at the human progress, hydrogen cars are coming out all over the place. How do they store it? Well, they store it in compressed hydrogen.
You know,
So-
there was a gas station, hydrogen station in Norway or Sweden.
Yeah.
Did you hear about it? That frightened a lot of people.
That what? That fried? What?
It exploded.
It exploded?
In Norway or Sweden?
Yeah.
I don't remember where.
Yeah.
It exploded and burned. So.
Yeah. Hydrogen sounds scary, but you can look at some videos of what happens, like with
It can happen.
tanks bursting.
Yeah.
But the thing is, when you have 100% hydrogen, when you explode that tank, it won't explode. It will do a high velocity flame and just kind of like leak out and flame out. It doesn't explode unless you have over 4% oxygen, in which case it's explosive. So as long as you're storing it pure, which you can control that process, then you can do it. So I'm definitely a fan of it.
For explosion, it needs some oxygen. It doesn't do
Hydrogen does not explode by itself. It has to be mixed with oxygen.
some oxygen.
And typically when you have a tank of hydrogen and it just kind of goes out, it's not particularly explosive. It's only when you've got oxygen within it already that you do.
Yeah. Then it may burn outside, yeah.
Yeah, but it's not as bad as people think, and definitely there's a lot of prejudice against hydrogen from the electric car industry. I do think it's quite doable, and it's completely decentralizable. Like, for example, you can take wind turbines in remote locations generating hydrogen, and you're piping the hydrogen to other locations. I mean, that could be a pretty benign way to go about it, about our energy and stuff. The current gas and oil pipelines, you can be piping hydrogen as an energy source in the future. So let's talk about embodied, energy density, just to get a feel for some other things. So down in about like natural gas, jet fuel, crude oil, those entities, including wood, like where's wood here? Biomass. I don't see biomass here, wherever that is. But we're talking about 40 megajoules per kilogram. So those are the units. Megajoules, I guess I won't get into the details of that, but joules are a unit of energy, like BTUs.
How it can compare with fuel? Like gas. Energy mass.
So the useful way to treat, so from joules you get watts. So a joule per second is a watt. So for example, just for this basic literacy in these numbers, if you see a number like gasoline has like 40 megajoules per kilogram,
40 okay.
Right, so you read the table here. What's it say? The specific energy means the energy per mass. You're looking at, there is wood. Wood is 18, so it's about half. Coal is like 26. Diesel fuel is like 45. So wood is like half of the standard. But take diesel. You got 45 megajoules per kilogram. So that means you can have, for 1 second, you can have, this is megajoules, 43 million watts for 1 second. Well, that's if you used it up all in 1 second, but a kilogram of diesel, you burn that over time. But so in an hour, so per hour, there's 3,600 seconds. So you convert those, if you divide the millions by 3,600, you're going to get how many kilowatts you will get for that hour. So what is that? So we've got about 43, do that in a calculator. You get 43 million, let's say 40 million, 40 with 6 zeros, divided by 3,600, which is 60 minutes times 60, so that's the number of seconds in an hour. So for 1 hour, out of a kilogram of diesel fuel, you can get 11,000 watts, so 11 kilowatts. That's a lot of energy. A lot of it. So each kilogram of fuel, each gallon or liter has, a liter has about 1 kilogram, a gallon has about 4 kilograms or so. 4 liters, 1 gallon is about 4 liters. But yeah, that's a lot of energy. So if you take wood, you've got 5,000 watts for 1 hour from 1 kilogram. That's
can
pretty
extract
significant.
all of it.
If you can extract all of it. So that can be burned as heat, but heat engines, internal and external combustion engines, go up to like your 30% maximum, and very easily you can get...
What's the heat mass of hydrogen?
What do you mean? Heat
Hydrogen,
mass?
How much heat
So-
can it produce? Watts?
Okay, so take hydrogen,
I wanna
so
compare.
compare hydrogen. So hydrogen is going to be at pressure, like in the high pressure cylinders that they will use for cars. You will have not liquid, but hydrogen at 690 atmosphere. So that's like 10,000 psi. That's the current state of art. That has 141 million joules per kilogram. So you got about 3 times as much. So for any mass of hydrogen, well, no, let's talk about specific. Well, this is per kilogram. So this is specific energy density. So per kilogram of hydrogen, you've got 3 times as much as diesel or
It makes
gasoline.
sense to use it.
Well, yes, it does. So that's why there is a huge case, when you understand the numbers here, there's a huge case for hydrogen energy, because when compressed, you can store a lot of energy in it. Your gas tank's going to be much smaller at that point. So if you look at the table, just the take-home message from it is understand the units of megajoules or joules per kilogram. So joules are a unit of energy, and watts are joule per second. So energy is joules. Watts, which is power. Power is how fast you're extracting that energy. So we said that we could get 11 million watts from diesel in 1 second, but in 1 hour we would get 11,000 watts for that hour. So you can have the same amount of energy. It all depends how fast you use it for the concept of power. So that's why when we talk about, for example, solar energy, the power that comes from the sun is 1,000 watts per square meter. So it's 1 kilowatt per square meter all the time. So in 5 hours, well, you take the efficiency of, so let's do a practical counting experiment here. Solar panels are 20% efficient these days, the ones you can get commonly. So say out of 5 square meters of the sun, you get 1 kilowatt of useful electric energy. How does that compare to the energy content of diesel? So basically it says that in 5 hours, well, we got 1 kilowatt. In 10 hours, you get the equivalent of 1 kilogram of diesel. So it's about 10 kilowatt hours, it's 11 kilowatt hours. But if you talk about thermal energy, that's the sun already, so you don't have to take that 20% ratio. So 1 square meter is getting 1 kilowatt constantly. So in a day, let's say the 10 hours or the 11 hours, you've got the 11 kilowatt hours. That's how much we just said 1 kilogram of diesel has in 1 hour. So you can see that comparison. So solar energy is not insignificant. It's quite significant. And of course you got much more chemical stored energy. I mean, you can take that 1 kilogram in a bottle in your gas tank, you can burn it up. For solar panels, you would have to have a big array to trap that kind of energy. But when you get down to it, you can take a look at, okay, if you got, say, 1 kilowatt of power coming from the sun, and you got panels that are 200 watts efficient, you can start looking at the feasibility of solar cars. If, like for example, they have the sun race and college competitions where they do solar cars, they're doable. I think if we get super smart with like plastic fiber composites with super lightweight bodies, I think solar cars could be feasible in a certain way for very light vehicles that can run on solar power. But we also talked about how even though the power is low, power means how fast you're doing something. So a solar tractor, which is autonomous, its power will be low so it will be moving very slowly, but it can do a lot of significant work when mixed with hydraulics, which give you the very high torques. Okay, time? 30 minutes? Okay, so we're about 30-minute mark, so I'll cover a few more concepts here. So energy density is a very important thing. So here we just compared hydrogen, say, to wood, to diesel. So the net present biomass, like in energy density, carbon, which is charcoal, that's also worth looking at. So for example, charcoal or coal would have essentially the same amount of energy. So where is charcoal here? Coal, it's not there, but coal is essentially charcoal. So that's got about 20 to 30 megajoules per kilogram. So that's like a little bit under gasoline. So, but you can generate charcoal as a renewable energy source. So the things that are important for us, things like hydrogen, the charcoal, biomass, and maybe some other things in that whole list. If we talk about renewable energy, let's talk about embodied energy, because that's a very important concept. So how much does wood have? How much does concrete have? How much energy do you need to use in order to produce it? That's a very important thing from the energetics perspective, because energy these days means pollution. Like in the post-scarcity economy where everything is solar and paid for, as in we have enough solar capacity now that we never ever have to burn any more fossil fuels to get the extra energy because we've produced the solar panels. In that kind of a scenario,
efficiency may go up. Even from 8 to 20, it may go to 40.
That's possible. But the point is, at all times, okay, just because we have free energy, it doesn't mean we should waste it, because it's always using things wisely is how you get yourself out of trouble. But the point being about embodied energy, currently energy that is used to produce things is accompanied with some pollution and negative side effects like resource extraction. So it's important to understand how much energy something has, and then you can compare. Like when I start to look at that more closely, concrete and steel make a lot of sense. And let's compare concrete. No, for the amount of for the longevity of that material versus how much embodied energy it has. Like how much energy did it take to harvest it and to get it for you to use it. So take a look at that. Like for example, concrete has 1 megajoule per kilogram. In other words, to produce, that's concrete, not cement. Is cement there too? Because cement would be just the plain cement without the aggregate mixed in there. So to produce one kilogram of concrete, you need. We said that diesel had, or let's take wood, or not diesel. Like how much gasoline is one kilogram of concrete? If it's one, that's about a 40th. So 1/40th of a kilogram. So you're looking at a piece of concrete that's got, like, you poured like a few drops, like 1/40th of a kilogram. It'd be like a teaspoon or a couple of teaspoons or something, a few teaspoons or tablespoons, however much that is. So that's concrete. What about steel? Steel is 20, actually. In other words, for 1 kilogram of diesel, you're going to produce 2 kilograms of steel for the embodied energy. That's pretty interesting. But look at wood. Where's wood? Which kind of blows me away because I didn't appreciate it. Where's the wood here? Plywood. Well, here plywood is 15. Where's the wood in there?
Plywood is there.
Who took? I saw wood here before, and it was rather high.
Timber.
Where?
Getting closer. 200 steel.
Oh, timber, 8.5. So timber is about 1/3 that of steel. Now this is assuming that you've got clear cutting in Canada and a lot of transport and so forth to the world. So possibly the timber equation for locally produced wood would be much better. But as you see, man, build that thing out of concrete, not timber, if you care about pollution. If you're going to be sourcing wood from Menards, because concrete has 8 times less embodied energy for its weight, and so timber compared to steel. Like before we had modern economy, we had wood everywhere. Matthew?
Does this take into account, for instance, the light that the trees are absorbing to grow in the first place?
No, it doesn't. This is just the extraction energy, embodied energy. So no, I don't think they consider that. That's not what embodied energy is. It's like if you find it in nature, it's assuming that's already there. So in other words, like the amount of energy, like with the heavy equipment that's out there to get out there to make the roads, bulldozers, saws, and the transport, and the sawmilling gets pretty intense. But I bet you, I'm sure you can do much better than that if you do local production of wood. Especially if, say, you're running a solar tractor. Well, it's still using that energy, but it's clean energy, so it will be much better. So there probably is a good case. But what's wrong with concrete? There's nothing wrong with concrete. Concrete is a renewable resource. When I thought about it, it's like, so first I was living in my mud hut, and I thought concrete was evil, but concrete is gotten from rocks. So you burn rocks, you get cement. Then the carbon dioxide that you burned off is absorbed back by the cement, and it's a carbon neutral cycle. So it's not too bad, but it is bad if you're releasing all those fossil fuels to make it. But then solar concrete would be awesome. So regenerative concrete, where say you got solar energy producing your concrete, that would be great. So let's look at solar concrete on a wiki, because I took a look at that. How much PV would we need to do that? There's some numbers there on solar concrete. Use PV to make cement from limestone. We've got limestone under this land. PV heats limestone, so you're using just thermal. You can do like either solar concentrator, which is hard to control, or you can generate PV, which is easy to control using wires and heater elements like nichrome. So what are the numbers? What's the bottom line? Embodied energy.
36 kilograms per day on 60 kilowatts.
Yeah, so you get a 10 kilowatt solar panel array. Oh, I was thinking about, let's get universities doing this so university students are making concrete. 60 kilowatt hours of energy per day. So 60 kilowatts gets us, 60 kilowatt. It's not a mistake there, not 60 kilowatt, we're talking about 60 kilowatt hours from a 10 kilowatt array. Sorry, let me correct that right now. 60 kilowatt hours, in other words, a 10 kilowatt array, something 3 times the size of what we have on the Seed Eco Home, that gets us 36 kilograms of cement. It's not bad for solar concrete. And of course, that's going to be within a system, it's going to be more expensive to do that. But our cost for our PV there installed is 1.5 cents per kilowatt hour. So we're actually, I think there's a case for completely economically feasible solar concrete production. So let's do it. We're going to do this here because I just think it makes sense, and we'll go more through the numbers. But the baseline is you got a solar panel array. We've got industrial production, like running a workshop with it. Say we get a workshop with panels on top. Like I'm thinking for a whole village or campus, you probably have like 100 kilowatts of solar, maybe 200 kilowatts. So if you say you dedicate one day to concrete production, you got to build a new building. It's actually doable. So that energy balance kind of comes out. So it's pretty interesting. Look at the numbers under solar concrete. When you understand the concept of energy and power, with a baseline of a kilowatt per square meter coming from the sun, and also with the efficiency of PV being about 20%, you can see how much area and how much solar concrete you can make for that area of usage. Interesting experiment. Just think about it and maybe you get inspired by it. So steel is about 20 megajoules per kilogram, so that's kind of important to know. Like basically, what's about 40? Flax insulation, cork insulation, glass fiber insulation. So when you talk about these energy intensive materials, you can kind of think about it heuristically. You're saying, okay, I got a kilogram of fuel, I get a kilogram of material. So next time you think about these materials, like say that's like 10 kilograms, well that's like 10 kilograms of gasoline. Like this overhead display for this LCD screen here, that's got 2 gallons of gasoline in it. That's quite a bit.
How much is for marble?
Marble?
Talk about marble. It's so expensive. I want to know why.
Marble 2.
Marble is only 2. So it's
God.
well because what
That's
that's amazing. Yeah. In terms of energy content, so basically you're cutting marble from quarries, which takes about 2 times as much energy as actually burning rocks to get cement. But
2 times less.
2 times more. It's 2 megajoules per kilogram versus concrete 1 megajoule per kilogram.
Okay.
But concrete, we're talking about the mix where it's cement with the aggregate. So anyway, okay. So moving on, let's kind of almost start wrapping up here. Specific energy is that per mass. So when we talk about energy density, we're talking about per kilogram. So you have to be careful whether you're talking about per mole, which is the per number of molecules, whether you're talking about per volume or volumetric energy density, or specific, which is per weight. So while like hydrogen at room temperature and pressure would be a huge volume, right, because it's the lightest gas, a kilogram of that will take a huge volume, but that kilogram will have 3 times as much energy as a kilogram of fuel. So then you have to think about, okay, you probably have to compress that in order to make it practical for you to drive a car with it. Now, one thing about hydrogen, people all talk about fuel cells to make it efficient, but we can make a case that if you decrease the cost of production of hydrogen, you can burn it in regular internal combustion engines to have a clean fuel. So if you can get, right now, people don't do that because it's too expensive. You wouldn't compete with gasoline. But if you have different assumptions like ecological integrity and other factors like decentralization or distribution of wealth, then using hydrogen will make a lot of sense. And that will come from forward-looking entrepreneurs who do that, less from ExxonMobil. Right now, fuel is getting decarbonized, so we're going more towards things that have less carbon, like hydrogen. So power, then you have power density. Like if you have power, that's the amount of energy you're using per time. Now, when you talk about devices that convert, like motors, how much power can they use per how big are they to handle a certain power? That's called power density. So that means power per volume. So for example, a hydraulic pump is extremely power dense. It handles, say, 20 to 40 horsepower in like a couple of kilogram package. An electric motor that's equivalent, that's 20 or 40 horsepower, would be hundreds of kilograms. So it's not as energy dense as hydraulics. So hydraulics have the highest energy density. Electric motors are second, and then combustion engines follow that. So just for reference. So here we're talking about how much mass is required to handle a certain power. Hydraulics are the winner, and for which reason they're very popular in heavy equipment, because they're small and provide you huge bang of power. Units, I won't get into that, there's too much detail. The biggest thing about units is that people came up with so many different kinds of units, like ergs for watts. I mean, there's so many different units, and a lot of times people don't agree on how to communicate them. Like sometimes people may, like BTU for energy content. Sometimes people will confuse things like kilowatt hours with kilowatts, where one is used for energy, one is for power. A lot of times people for torque they will say pounds of torque.
It's pounds, foot of torque.
It's pounds, and people.
No, it's
So for torques, like inch pounds, foot pounds, kilogram meters, Newton meters.
There.
There's like 20 of them, and you have to convert. So you have to bite the bullet somehow and say, okay, I'm going to use one that's convenient for me. There's many of them. PSI is very common. I mean, we're just using PSI here.
Pascals.
You can use whatever. So I will just say that when you see units out there, it's probably wrong. Like if it says pounds, it might mean like foot pounds or whatever. Like be very careful. Unless you understand it, it's probably not saying to you what it's really saying. So that's the only thing I will say about units. They're hairy. How do you measure units? For us, relevant in a shop are tapes on the millimeter scale, like tape measure. Dial indicators are very important for us, which measure thousands of inch or like tens of microns. If you go down to nanoscale, you've got
Glass scales.
glass.
BRL on the mill.
Yeah, how do you do that? That's waves. That's optical, right?
It's a glass. Well, it's a glass scale, so it's etched, and it is optical. It looks for and it
Counts the number of lines for digital readouts. Is that what it is? Then you get interferometers, which means that at the nanoscale, only things that are that small are light waves or energy waves. So you're now measuring how waves interfere, how they bounce back from a surface. So you can have a laser. A common thing is a laser-based distance meter, which actually counts the number of waves from a certain surface. So that's kind of beyond our scale because we're not at nanoscale. But dial indicators, what's a dial indicator? It's a device that looks like this. It's a very precision thing that it has a little indentable structure there, a little poker that the distance you poke it makes it show up on a dial. And these things are accurate. You can clearly see like 1,000th resolutions. So that's pretty much as crazy as we get currently to get precision machining happening. But beyond that, I don't know yet what happens. Like if you go to measuring microns when you do air bearings, like how do you measure that? That gets to the next realm of technology. Typical values, it's useful to know certain values when you use tools practically, like values of like RPMs come to mind. Like how fast does a wheel have to spin to get you a certain speed? How fast does an engine spin? That number is typically about 3,600 or 60 hertz, which is 60 revolutions per second or 3,600 per minute or revolutions per minute. So when you talk about engines and motors, you're talking about the thousands of revolutions per minute scale. For example, for the cordless drill that we'll design, it'll be between 0 and say 1,000 or 2,000 RPM or such. What does a table saw do? It's probably about 3,600 RPM. Like the metal cutoff saws that we use, I think those are like 5,000 RPM. Little grinders can be pretty fast. They're very fast, like 5,000, 10,000 RPM. It's important to kind of have a feeling for that because when you're designing a cordless drill and you get an off-the-shelf motor that spins much faster, you're going to have to know how much you're going to have to reduce it to make it go at a useful speed. So you have to be familiar with what a useful speed is. And you can picture that in your mind, like kind of have to start getting a feeling for what RPMs are to get an understanding. Otherwise, those are just numbers. But when you think about it, think, an electric motor, well, that's 3,600 RPM. A wheel on a car, that may be like 500 RPM. A slow-moving tractor that may be like 10 RPM or something. So those numbers you have to know, because when you buy a hydraulic motor, you look at its RPMs. Like it might be, for a wheel hydraulic motor, the max RPM may be like 150, which gets you to like 10, 20 miles per hour in a common situation. So you have to be familiar with those, because when you're sourcing parts, you need to be familiar with that enough to predict its performance, and so you have to calculate those kinds of things. What about voltages? Literacy in voltages. What kind of voltages are relevant? Relevant is quantities like 48 volts, which above that it's not safe to touch. So anything below 48 is relatively safe. What's the basic unit of voltage? Voltage comes from electrons, so the particle is called electrons. That's what creates voltage. When you have voltage at the basic level, at the chemical reaction level, that's on a unit scale of like 1, 2, or 3 or so electron volts. Matthew?
I was under the impression that if, for instance, your hands are wet, that the safe voltage changes, like lower voltages can become unsafe. Is that true?
Yeah, it's true. It's essentially, when are you conducting as opposed to that voltage going through something else that's more conducting. I would say for like, I think I heard the number 48 be pretty safe. I haven't really explored that too much.
I thought ampere is the problem, not the volt.
Right, but it has to overcome the resistance of the air.
Oh yeah.
It's the amperage, but voltage will determine, right? The voltage.
Resistance is constant, more or less. So yeah, voltage will determine.
Yeah, voltage will determine how many amps you're going to send through something. So you can get into like milling speeds, like how fast does a bit have to spin. Like for example, the other day we mentioned if steel is 50,000 psi and you're taking off at 1,000 RPM or at 1,000 RPM, if that's the spinning rate, you're taking off. We did an experiment saying that 50 pounds. If you move over 1,000th, I'm losing my train of thought on that. But basically, in milling, depending on the speed that you have, depending the speed, that's a combination of speed and distance with which you're going through material. You will be able to calculate how much force is required to do that based on how big chunks you're taking off the material. That's a very basic concept. Obviously, if you're going fast, then a drill bit or a milling bit with a certain speed will take larger chunks. But if you increase the speed of that bit, it will take smaller chunks, and you will be able to use less force to do that machining. However, the power will increase there, the power requirement, because moving faster means you're using more power, because power is energy over time, how much energy you're putting into that over time. So you kind of have to get a handle of all these quantities. What else to say? Yeah. There's a lot of different things we can talk about here in terms of force, power. Units are, but understanding the quantities, like looking into forces that come from, there's forces that come from just about everything. Like electricity will have forces associated with it when it interacts with other particles, like magnetism, electricity that creates forces, gravity creates forces. There's pressure, force of pressure. There's thermal forces, like the velocity of particles moving has a temperature associated with it. The velocity of particles hitting, say, in a container, that's pressure. There's many different quantities, but they're all based on fundamental things like mass, distance, and time. What else is there? An electrical charge, because that gets into electrical forces, and then nuclear charges when you get into nuclear energy. So out of like 5 super fundamental quantities, you get all these different pressures, magnetic forces, electrical forces, speeds, velocities, powers, time, distance, and mass. That's primarily what we're interested in mechanics. And when you talk about electric quantities, then you also talk about charges and voltages and magnetic fields. But there's only so many quantities. So if you think about this, to wrap your head around all the different quantities that are out there, you have to think about, okay, there's ultimately, like, what's the reality underneath it? It's matter, it's time, it's distance. And the combinations of those for mechanics get you all the other properties that we just talked about. And there's particular equations that are associated with other quantities, but for a general overview of this, I know I can do much better on this lesson, but that's a general overview on force, power, and energy.
Do you have all those equations on there? Or are they easy?
Good thing to do is, like, when you have a question, like Google really works well, like, how do you measure the force that of a hammer? How do you measure the energy that a car requires? I mean, all this kind of stuff, you can Google it and start thinking about it. I think that one of the most useful tools is just thinking about what are the quantities there and trying to approach it from a fundamental perspective, because then you can have insights. Like the only thing I can encourage you is to get the insights of understanding the quantities like embodied energy. But once again, take embodied energy. That's still volumes, so distances, like mass times acceleration is forces. So it's always masses times and distances. So when you have this embodied energy, or like, for example, if we ask ourselves, can we store hydrogen to run cars? Or can we do gravity storage on our site to provide electrical power at night? It's all quantities of mass, time, and distance. So if you can get your head around that, you can get into the more specifics. But from the most generalist perspective, it's all there is. Like, if you want to calculate whether a pond is feasible on your land, it's mass, distance, and time. If you want to figure out what kind of hydraulic motor you need, fundamentally it's mass, distance, and time. So you have to be able to kind of understand it at a very fundamental level, because all the different units and quantities derive from those fundamental properties. So sleep on that and get insights to that, and then you can start proposing things. Because I guess the big thing in the mainstream system, you only get exposed to the things that everyone's talking about. But once you start thinking about these things, you get to understanding that, wait a minute, there's this other possibility, and then there's this other possibility. So it's very important to understand this, because it leads to new options. And that's the general theme of what we do here, is we open source know-how so that new options are provided to people. So I think I'll leave it at that. So any questions from anyone in the audience or in the live here? Yeah, write down the book. So the question on the book that I quoted, the book you have to read to get further insight into this is by Amory Lovin's Soft Energy Paths. This was written decades ago, but it pretty much lays out the case for what sustainable energy would look like, and I think it's quite relevant today. Amory Lovin's, so I typed it in, yeah. So Amory Lovin's, Google that, Rocky Mountain Institute, and that is the seminal work, RMI, Rocky Mountain Institute. Amory Lovins consults to governments and at a big scale, but he's pretty much laid it out, like renewable energy is it, and a lot of people are starting to listen to him. But it's about efficiency. He has a big case for efficiency, because if you don't use it, you have more, and we can be way more efficient on things that we do.
So the advancement in storage, what does that trajectory look like, or what has the recent advancements been?
I would say that we're going to end up with a hydrogen economy and task done.
What do you mean by that?
What I mean by that is that you can generate hydrogen from water
Yeah.
using renewable energies. A lot of people think that we can't store it, but using today's technology, we already can store hydrogen. So what you just asked is, how do you store stuff?
How do you store?
Well, people think that it's batteries that are needed to store things. No, batteries are not sustainable according to current technology. Lithium at current rates of use has 200 years, and if the electric cars really take off, it's going to be decades before all the lithium runs out and we destroy all this land for mining it. So why not use common, widely abundant resources like water to do the same job?
You store the energy in the form of hydrogen.
Store the energy in the form of hydrogen. So you get hydrogen and oxygen. The oxygen you use for processed gases like cutting oxygen for torch tables or many other industrial processes, and the hydrogen you use as an energy source.
You are right.
So how would you turn like solar energy into hydrogen energy and then back into energy and use it in something?
Right. So the simple cycle there is you take wind energy, solar energy. It's called electrolysis.
Electrolysis.
Yes. So electrolysis is that you're sending a voltage through water.
Why
That-
we don't use electrolysis right in the car when you are driving?
Because you need something to power that electrolysis.
One battery.
You're plugging the power cord into itself. What I mean by that is, if you're going to have batteries, use the batteries directly. But batteries are not
Or you mean
particularly sustainable.
But that
So you
electrolysis.
so you've got wind power or solar power in a small subsection of the Sahara that provides all the power for the world. That's all that's needed, just a small section of the Sahara. You generate hydrogen, you pipe it through pipelines like you have pipelines for oil and gas, and you deliver that to everybody. How do you use it? The easiest way to use it is to take an internal combustion engine or a jet turbine. You can burn hydrogen in a regular engine. Did you know that?
Yeah. I
Yeah.
thought it was a regular engine.
It's pretty much regular. It has to be hardened, like for
Pressure.
hardened, because hydrogen does hydrogen embrittlement over time, and so you might have to replace some of the components so that they don't get hydrogen embrittled. Because hydrogen embrittlement is a real thing. When hydrogen goes into, it's such a small molecule that when it goes into steel, it weakens it. So you have to use more advanced materials or ceramic parts or something else. So you're burning hydrogen in something as simple as an engine, and then if you want electricity, you can that engine could be in your car, so you're driving, or that could be a generator, so you're getting power for your house. This is it, people.
How do you, is there anything, where can we find information on how to build one of those small scale? Like, is that a thing?
Solar Hydrogen Chronicles. It's on a wiki.
Okay.
That's a seminal book on the topic. Walt Pyle is one of the authors. I visited him. So Solar Hydrogen Chronicles. HIandsolar.com. So that's Walt Pyle. I took notes.
What was the website again?
Go to Solar Hydrogen Chronicles. The website is HION solar.com. There's a download on the front page. Solar Hydrogen Chronicles. That tells you how to produce it, how to store it, how to use it, and the guy is relatively open source. I want to get him for a workshop so we can build one of these things. 'Cause, I've been out there to visit him. Great guy. He meditates. He's on a different wavelength. He's an engineer
Where does he live?
around Berkeley.
What state is that? Pennsylvania?
California.
In California, yeah. But that to me is a pretty seminal book, I would say. It's a very practical guide. Shows some of the projects that have happened, the work they did. Completely feasible. It's just, I think it's more about human consciousness to wake up to the opportunity. People don't know about this. People do not. Matthew?
So now, if most things went to hydrogen, would we still use batteries for things like cell phones and laptops and stuff?
There's a case for that, probably. Maybe if it's small devices, and maybe when we come up with better kinds of batteries. For the Global Village construction set, we have the nickel iron battery in the set, because that's a battery that pretty much lives forever.
Yep.
The Edison battery,
Edison
and pretty much developed first by Thomas Edison. There's batteries like that if you unearth it from somewhere, some people that bought that, you unearth it and like use it right now, it'll be like 100%.
Yep.
It's crazy stuff. It's DC. Batteries are DC. So nickel iron is good. There's always advancements in materials where if you have like carbon nanotubes or whatever, like your advanced material science at the level where you're actually manipulating atoms at the atomic level, which is going to happen pretty soon, you can come up with all the kinds of different chemistries of batteries. So probably in the future we might come up with something that's probably safer than lithium or less scarce than lithium. It's more about scarcity there. Things like nickel and iron. Nickel and iron are relatively abundant in Earth's crust.
But the energy
So-
mass is very low.
It's that, but they have new ones that are actually very competitive. So that's when you get into the modern version of the nickel iron battery. But no one's developed a modern version of the nickel iron battery since Edison took it. So that's definitely a point of development to do. Yeah, no, it's solar hydrogen. That's what, for example, Amory Lovins proposes, and to me he's the seminal figure in the field of energy. If you're paying attention to energy, you're following Amory Lovins. I mean, he's laid it all out, but just nobody knows about it. People don't listen to it, and there's special interests that aren't interested in listening. So we have to wake up to the opportunities. Yeah, but definitely very exciting. I mean, this is. That's why, like, okay, getting the enterprise up and running here, then we can do all this stuff and build that into the global open source village infrastructure. So right now we don't have the capacity to do all these projects, but as we grow, just you and me, baby, and the rest of the world, we're gonna do it. So, yeah. Any other questions on this? Okay, so let's go back to work and build a heavy-duty CNC mill and finish up the printers. We're almost ready to print on the printers. I just got to connect some more wires so we can start running. Okay, so we can start printing. Thanks everybody in the remote. We'll continue again tomorrow.
Oh, did you do a bunch of SPIs during that time?
I'm not doing that.